Hey everybody, welcome to today's lesson. I'm glad you were able to make it. Here I have on the screen two equations, r equals 2 sine theta and r equals 2 sine theta plus 3. Those two equations don't look very different from each other. Number one, we've actually already studied, but we haven't seen anything like number two. I wanted you to think for a minute. If you try converting number two into rectangular form using strategies we've already done from previous lessons, what would happen? So would you take a couple of minutes and you could chat as you're going along with any observations about one or two? Would someone type into the chat window, what happens with number one? That's one that we did last week. Okay, and I see some people responded that it becomes a circle, x squared. By multiplying both sides by r, we get r squared equals 2r sine theta, which turns into x squared plus y squared equals 2y, which we could go further with, but that's why the graph of r equals 2 sine theta was a circle. And maybe you remember that it wasn't just a circle, but it was kind of oddly a circle and then a second circle on top of the first circle. Kind of strange how that worked, but it was really two circles that were right on top of each other. Now, when you throw a plus 3 at the end, we run into a problem. Doesn't it? Why doesn't it just make a plus 3 here? That wouldn't be so bad. But it doesn't. Why not? That's right. The plus 3 would turn into a 3r here. So we'd end up with this extra, I could maybe square both sides again to get it to be an r squared, or maybe I could just write square root of x squared plus y squared. Suddenly this thing is looking pretty complicated. It is no longer a circle, and it's actually not going to be any shape that you've ever really seen before. And today's lesson is about equations of the form r equals a sine theta plus b and r equals a cosine theta plus b, where b is greater than 0, and where a could be anything. So we're going to see what happens with curves like that, what they look like, how to analyze them, things like that. Now, the first warm-up question was r equals 2 sine theta, and I want to show you a little strategy that we actually never used this before because it really wasn't that necessary for understanding all the curves we've seen so far. And it is to graph the polar equation on a rectangular grid, but instead of x and y, you have r and theta. And if you do that, well, it's going to be a sine curve. Here's 0. I can't see this too well. 180. I think that's the iPad I'm writing on is small, and my eyes aren't that good. But I'm hoping that whatever. Let's just say 360 is over here, and 180. So that is what the graph looks like on a rectangular grid. And we haven't had to do this before because normally the rectangular, what happens if you change r into theta, I'm sorry, r and theta into y and x and graph it on a rectangular, that picture is usually like really complicated looking and not that useful. But for these curves of the form we're going to look at today, this is going to be one of our best ways of analyzing it. Here it is on this one. And if you downloaded and printed out the picture, maybe you have like a nice drawn to scale one. Now here comes the new idea. So here I have side by side the rectangular grid, and this is with theta and r. That's the rectangular grid. And on the side, I have a polar grid. And this strategy is going to help us for today's lesson and then also for 2 days from now. Again, we haven't needed it. We haven't needed it up until this point. So first of all, I'm going to make red. And that point there, if I translate it onto the polar graph, is going to be at the pole. And then, oh wait, hold on one second. Sorry about that. Now, as I, you know what, I'm going to throw second points on here and make it blue. That point there at 90, 2 would be somewhere over there. And I'm going to make a green point also. That point there, any point that has that's on the x-axis or the theta axis in this graph will end up at the pole in the other graph. Now, if I make all the points from here to there, from 0 to 90, that thing, remember how a straight line, remember how r equals theta became like a spiral? That's kind of what's happening here. It's getting, the r value is getting bigger and bigger as theta gets bigger and bigger. And that's why that starts to happen. And then if I make the blue, this entire thing, with that, as theta gets bigger, r gets smaller, and that's why it kind of like spirals inward. And that's why we get a circle. Actually, just for the first 180 degrees of the sine curve, we see that that circle there. But if I were to keep going and make this green line segment go all the way down to there, this point, which I'm going to make another color, That yellow point is at 270 -1, which is actually right here again because it's going backwards. So my green line, and this part is a little tricky to see, but if I'm at like 181 degrees, which is actually pointing in this direction, but because it's negative, I'm going backwards. So I end up back on that line. And then as I continue going through up to like 207, 260 degrees, let's say, but I'm going backwards, so I end up back. And that's why this green retraces over the red and finishing out this entire yellow thing would end up like that. So that's the idea, just revisiting r equals 2 sine theta, but with this idea of looking at this kind of hybrid rectangular graph and comparing it and kind of seeing, and it is confusing because there are points that are not unique, like this point and this point graph to the same position. So it is kind of strange the way that works. But this type of analysis is going to help us do the more complicated equations. Because now we're going to get to see in the warm-up question, it was 2 sine theta, r equals 2 sine theta plus 3. Well, over here, I'm going to compare it to 2 sine x plus 3, which is a sine curve that's been shifted up. Now, one thing about this graph is that it has no x-intercepts. Someone type into the chat, because this graph has no x-intercepts, what is going to be true about the polar graph of this? Yes, and I see a couple of people wrote, nothing, it's not going to pass through the pole at all. Now, let's take a look if I do this like 1 point at a time, just to get a feel for it. The initial point is here at 0, 3. So that's going to be like over here on the polar graph. And then it's going to go up to 95, which is like over here somewhere. And then it's going to come down to 180. It's going to come down to 183, which is going to be somewhere over there. So you might start thinking, okay, maybe this is going to be some kind of ellipse or something like that. But not quite, because here's where it gets a little bit unusual. At 270, it's down to 1. And this is where it gets tricky. You might still say, oh, maybe it's an ellipse. Let's move over to I'm going to put up Desmos, so we could actually even better than Desmos. I'm going to put up Mr. Stern's grapher. Here we go. Let's see. Yes, and I posted this. I actually added this to my the GeoGebra book for the class. So let me change this to 3. Oops. Load it up first. Okay, so on the left, you can see the rectangular graph. On the right, check this out. And this is really neat and fun to do. I'm moving this point around, and watch. It goes up, and like I said, it would hit 5 at 90. It would come down back to 3 at 180. But look what happens in between. It's not going to make an ellipse. It's going to make a kind of surprising thing. Where it hits its low point. And then that happens. So this thing is not a circle, and it's not an ellipse, but it has its own name, and it's called a limacone, which is spelled Limacon, but the C has like a French accent in the bottom. Anyway, this thing is really neat to kind of play around with. You can kind of move it around, and you see how he made it so that it graphs the individual points. It's not that clear, like, why is this going like that and then going out again when it's getting smaller, but it has to do with like the way the angle's happening. So anyway, it's kind of surprising shape, but that's the shape that we should expect, at least in this type that has no x-intercept. I think this kind is called dimpled limacone. It's kind of like a circle or ellipse or something. And if I change this b value to be bigger, it becomes more looking like a circle, less dimpled, but it still is officially a dimpled limacone. And that's true. Whoops. That's true as long as B, make a note, if B is bigger than A, so that the rectangular one does not have any x-intercepts, you will get this dimpled limacone. But let's see what happens if B equals A. Oh, and I see some good observations. I just finally got to see the Mandelbrot set. And yes, it does look a little like a peach. What happens in this second situation? Here's a scenario where B and A are equal to each other. So yes, I see it will go through the pole. And the bottom, I hear the word converges at the pole. Check this out. I'm going to move the points around. And we can see, just like before, it hits the peak. It goes back to like the starting point. But now check out what happens. It spirals inward to the pole, and then it spirals outward away from the pole. And because that looks like an upside down heart, this shape is called a cardioid, C-A-R-D-O-I-D. So cardioid is when B equals A. If I make A equal to 3 and B equal to 3 also, oops, I just gave away the, I get a different cardioid. So that's called a cardioid. It's like upside down heart. It's a limacone where B and A are equal to each other. But the most interesting thing that can happen is when B is less than A. Okay, because when B is less than A, sorry, when B is 0, that's an example of B being less than A, but that just becomes a circle, really 2 circles. But if B is bigger than 0, oh, and I always make B positive. I always make B positive because when B is negative, it gets a little bit confusing because it ends up looking like one of the other curves. I'll talk about that afterwards. So B is 0, it's a circle. B is bigger than A, it ends up becoming either a dimpled limacone or a cardioid in the case where B equals A. but B is between 0 and A, something kind of surprising happens and I think kind of interesting. So let's look at this example. 3 sine theta plus 2. And for this, I think I'd like to go back to the iPad because this is really this is like the big instructive example for this lesson. So let me do this and come back to that. Okay, iPad should be appearing. There it is. So this is the major instructive example of the day. And I'm going to use actually a whole bunch of colors here. I'll start with red. So my starting points going up to here. Actually, I'm going to make that ending point a different color. Okay, so the blue point is at 93, 90,3. The red point was at 90,1. And it's going to sort of spiral outward, kind of like we expect with these limasones. Then the blue, I'm going to go down to the 180 point. Actually, yeah, we go to the 180 point. Not going to go all the way down to the x-axis. You'll see why in a second. Let me make this thing a different color, perhaps green. So that green point is over here. And the blue is kind of spiraling inward. But now I'm going to make, how many colors can I choose from? Okay, I'll go with this purple. So I'm going to have the green line go up until it hits the x-intercept. So that green line goes like that. And this is the most confusing part because it's going to spiral inward. This is like from 180 to whatever that that theta is. It doesn't matter that much, at least for today's lesson, but it's going to spiral straight into the center. And now that it's at the center, it does get a little confusing right here. I'm going to go with this other. I'm going to make this point here, this other kind of purple color. So that one is at 270 -1. So that point is going to be right here. So this purple line, this one, goes like that. I want to explain that a bit. So this this angle where this starts to happen, I don't even know exactly where that is. It's somewhere between 180 and 270. Let's just pretend it's 230 degrees. So at like 230, we're pointing this way, but we're going backwards. And that's where this starts happening. And if I continue from here to the next x-intercept, it's going to go like that. And that's because I'm facing now in this direction, but I'm going backwards. And the final piece of the puzzle, I'll make this some kind of orange, is that going back to 360. That's going to finish up this. Okay, that didn't look, let me get the official picture now so you can see this a little better. But this thing, this shape is, it's called a Limbasone with inner loop. So I'll write that down. There's like a little accent there because it's a French word. It is French for the word snail, or it used to be or something, but because this thing looks a little bit like a snail. Let me bring back the great Mr. Stir graphing Limasone's webpage. And yes, somebody asked, this only happens if B is less than A and B is greater than 0. Well, if B is less than 0, it actually happens also, but I'm not going to be making B less than 0. I'll show you why afterwards. So here we go. Check it out. This is the real instructive part right here. Okay, it gets to the peak. It comes back down at 180 degrees. And now check it out. It's spiraling towards the center. And oh, Mr. Stir just added a new enhancement. You see how it's red down there? Well, this draws that red also. And finally, like that. So that is Limbasone with inner loop. And I encourage you to bring up this web page and kind of move it around and get a feel for the side-by-side comparison of the rectangular. If I change this to be, actually when you, yes, excellent point Leo just made. When, see, as B gets smaller, the inner loop actually gets bigger because the inner loop is this piece below the axis. So that's the piece that becomes the inner loop. That's smaller than the piece above the axis. But as it gets to like 0.5, see the inner loop and the outer loop are almost the same size. And then finally, at the point where the B becomes 0, the inner loop overlaps with the outer loop. So it's fun to kind of here, you can see basically the whole lesson there. There's the circle, Limbasone with big inner loop, Limbasone with small inner loop, Limbasone that became a cardioid, and then a dimpled Limbasone. So I highly recommend you like move the slider around. I think I made this in, let's see. I think I made it in Desmos also. Where is it? Oh, it must be in the same. And you can see, you can mess around with A or B and see how that inner loop happens. Okay, what do you think, what do you suppose happens if I were to change, make a change here? Let me bring this point back to the beginning. And what do you think happens if I click on this? And now it's cosine curve. Take a minute to think about what will happen if I change the sine curve to a cosine curve. What predictions do you have for that? Okay, very good. I see a lot of people said it rotates. And that is what ends up happening because in a cosine curve, it starts at its high point. And then the inner loop is going to happen at its low point. So the inner loop happens that way. And that's what happens when you change sine to cosine. It basically rotates 90 degrees. And then you can mess around with changing the B value. B becomes 0. It becomes a circle again, two circles really. The inner loop's the same size. Here the inner loop is smaller. And when I get here, it turns into a cardioid that's sideways. And then it becomes dimpled Limbasone. Okay, another question for you. What do you think happens if A becomes negative? Think about that for a minute. What do you think happens if A becomes negative? This is still sine, by the way. And good, that's right. It is going to get reflected. Here it comes. So here's dimpled Limbasone, but the dimple is going to be on the top. And a good thing to do, if I change this to 2, so A is not equaling B, but B is equaling absolute value of A, we do end up with actual heart-looking heart, a cardioid that's facing in the way we're familiar with, -2 sine theta plus 2. And the fourth possibility is if it's a negative cosine curve, the dimpled part or the inner loop is going to be on the right instead of on the left. So those are the 4 things that can happen. Now it's true that B can be negative, but something kind of surprising happens. Actually, let me come over here. Let me, hold on a second. Let me go to Desmos. I don't usually make B negative, but I do want to show you. Here's B equals 1. This is 2 sine theta plus 1. And I want to make a prediction about what happens when I change the plus 1 into a minus 1. Prediction about changing the plus 1. Very good. I see someone said it stays the same, and someone says the 2 loops swap, which are both true. When you make it into -1, it does look like the same picture, but actually the inner loop got graphed. If I were to graph it like on the TI calculator, it would graph the inner loop first, and then the outer loop, because, well, does Mr. Sturs let me do that? Let's find out. Does he have B equals negative? Yes, he does. So if B equals -1, and this is sine, and A equals +2, and if I move this point around, oh, well, I am right. It does graph the inner loop first. Up here, that little piece is the inner loop. Not immediately first, but it graphs the inner loop before the outer loop. But it ends up looking like the same picture. So it's kind of confusing. That's why on like a test and on the Delta math assignment, I'm always making B positive. Okay, I'm going to finish up today with 2 challenging questions for you. Get the iPad back going. Oh, someone said this is not how it is in Delta math. No, it's not. It's not A sine theta plus B. Jonah, how is it? Oh, you put plus in and it says negative. Okay, so there might be a problem in there. Do you mean B could be negative? Ooh, that's not good. I will need to fix that. Thank you for letting me know. Yeah, I made instructions on it to only do plus for B, and for your answers that you type in to do plus for B. But so I'm gonna have to double check that. I just made that. Okay, the last 2 questions for today is
Can you go in the other direction? So is this going to be sine? Is it going to be cosine? Assuming b is positive, what would produce this graph if b has to be greater than 0, but a doesn't? What do you think? You could type in your answer for this one. What are some clues? This is a really good question to think about. Okay, Jonah, I will fix up the delta math. Would someone type, is this one going to be a sine or a cosine one? Okay, yes, this one will be a sine. And now it's just a matter of what two numbers to put there. I see 4 sine x plus, someone else wrote 4 sine x plus 1. Someone else wrote that also. A sneaky trick for this is, you see 5 is the high point. Well, the high point is going to be a plus b. But the low point is going to be a minus b. Because at the 180 degree mark, sine is -1. So then you can get 2a is equal to 6. Wait, hold on a second. Now I got myself confused. Sorry, it's a minus b equals 3, because that's kind of this low point. So 2a equals 8, a equals 4, b equals 1. So that's like a sneaky trick for figuring out. So just by based on sort of the peaks, these two peaks, you're able to figure out a and b. And here's another one for you. This one's got an inner loop. What do you think? What do you think this one is? Oh, we're not able to see where that number is. That looks like it's at, since this has radians, this is -1, and negative pi is -3. This must be -6. Oh, more like -5. Okay, so type in what you think the equation is for this one. Well, I do see that it's going to be negative cosine. And the question is, what's A and B? 2 is definitely involved because it's kind of like A plus B is kind of like the number 5 if you ignore, the whole negative thing. And A minus B is kind of like 1. It's kind of how far away. We're taking sort of absolute value here. So 2A equals 6, A equals 3, and A equals 3, which makes B 2. But the negative is actually only in front. Well, for delta math, that's what I was thinking. Although I suppose even if that other, it doesn't matter if that b is negative, but I would say use positive value of b, and then the answer would be -3 cosine theta plus 2. I'll go back to the delta math to convince you of that. further. So this is cosine, and I'll make it -3. And +2. And you can see it does agree with that picture. And you can watch it get drawn out. You see it starts with a portion of the inner loop. I should like that. Starts with the inner loop, then makes the big loop, the outer loop, and then makes the other half of the inner loop.